So first of all, I'm happy to see a lot of people online. This is a course that is intended without any specific background. Therefore, it might be a bit difficult for me to address the needs of everyone. We will see how this works out. But I would like to ask everyone to use the chat channel and write questions and or requests there so that I might be able to adjust my speed or style accordingly. So my first question is if my slides are visible.
Yes.
Yes, the slides are visible.
Okay, thank you very
Yes.
much. Okay, great. Now we tested both the chat, the mics, and also I saw someone raising their hand. So seems, luckily the technology seems to be working fairly well. So then I would like to start, and the first thing I would like to talk about is what topics and questions we are going to touch on in this introductory lecture. So first of all, it's going to be about the definition of intelligence, and most specifically, what we mean by artificial intelligence. And this is not as easy as it seems, or, well, some of you might expect that this is not an easy definition. Then we could ask the question how it works. We can also ask how to create it. And of course, this is what we are going to look into in the upcoming lectures. You might want to know how to control, repair, or improve it, especially if you heard about the fantastic ideas that the media usually comes about with the artificial intelligence going out of control and doing very unintended things. So the last question or question group that I would like to highlight is that if we create an AI, and AIs do exist, as we can all see it and experience it in the world, what the consequences are going to be. Do we need to be afraid of it? Will AI replace computer engineers or anyone else with any other profession? And what can we do? So one more slide as an introduction about why I think it's worth studying artificial intelligence. So first of all, to get to know the components that are required for intelligent behavior. So these are different aspects of AI, including rationality, including learning, including appropriate representations, and a number of other things. And as a surplus, if you do study AI, you can also understand some of your own intelligence, which is mostly instinctive intelligence, because we don't get specifically programmed, at least not in a human readable way. But seemingly as of now, whatever artificial intelligence system has been created, there were always people who managed to find themselves more intelligent in some aspect than those machines. So a few words about the administration. So as I mentioned, my name is Krzysztof Koroch, and you can reach me at this email address. Please feel free to contact me anytime, even outside the lecture hours. I will try to assist with all your doubts, questions, and comments. There will be some other instructors in this course, Professor Anna Garancsér-Horváth and Professor András Horváth, and the classes will be held here on Teams throughout the week, all workdays, each day from 3 to 5. Then this is Central European time, as Professor Exarchos earlier clarified, which is important for those who are outside this time zone. So if you heard about AI, the most obvious thing that showed up on media recently was the appearance of large language models with the announcement of ChatGPT towards the end of 2022 by OpenAI, which is one of the largest organizations in the world that deals with developing large language models and all sorts of intelligent algorithms, but this is what they are mostly known for by the wider audience. And this has been followed by quite a rush the upcoming year in 2023. Here you can see a list of all the models that were announced the next year, almost without a month in between them, without larger announcements from one of the companies. And you can see in the parentheses who the major players announcing these models were. So Meta announced Llama, one of the first open source models, which has been around since then. Then OpenAI announced GPT-4 later, and the same day Anthropic announced Claude, their model. And this is not that much well known, but it is pretty much comparable in strength to the OpenAI models. And just a few days later, Google also announced their large language model called Bard at the time. And later on, newer versions of these started appearing, and Apple also stepping into the competition towards the end of the year with an open source model. And then Google renaming their model to Gemini. And in 2024, the rush continued, and you can see that even the past months, a couple of new models have appeared. And actually, there's a typo here. Sorry about that. So this is Llama 3.2, actually. But step by step, companies are improving them. Now, a big question is whether this rush will go on. So the improvements are getting somewhat more incremental. So in contrast to the large quality improvements in the first updates, now these are more, I mean, there are multiple opinions about the quality improvements in these steps, but definitely the announcements keep coming. So I wanted to start with this because this is the most obvious thing that we experience from AI as in the general society. But now, with having clarified this, I would like to go back to trying to define what intelligence is. And of course, I'm going to turn to some very clever people who already gave a number of definitions. So one definition from an American psychologist and psychometrician from Professor Sternberg says that intelligence, looked at in one way, is something we all know what is. but looked in another way, no one does. So basically doesn't give too much, but it already puts on the table the big elephant that this is something really hard to define. Now, if we look at the word itself, it comes from Latin, and it means to comprehend and to perceive. And if you are thinking about an intelligent behavior, that must include these things, as well as sensing, reasoning rationally, learning and discovering. And if we put multiple intelligent entities or creatures in the same environment, then they will also need to be able to compete and communicate and cooperate. These are all different aspects of intelligent behavior. So with all these observations under our belt, we can try to come up with an actual definition. So on the third try. And here I'm quoting probably the most not the most intelligent, sorry, the most famous definition for intelligence, which says that the intelligence measures the ability to adapt to change. And this is a quote most frequently attributed to Stephen Hawking, but that is not quite true. He was not the primary source of this. He also quoted this. And according to historians, the first appearance of this definition was actually in French publication by Alfred Binet in 1905. So based on all this, I would still propose a fourth iteration for the intelligence, the definition of intelligence, which is used mostly by engineers. And it says intelligence measures an agent's ability to achieve goals in a wide range of environments. Now, by the time we get to this definition, it kind of feels that we're losing the actual message, because if we want to make it general enough so that it includes everything and we can't find a catch with it, but this is a tiny bit too general. You might even ask what an agent is. By an agent, we mean anyone or anything that is able to perceive and act. So this is what we mean by an agent. And this definition will also implicitly include some further things, which we can write here to make this general definition a bit more specific. And this implicitly has to include the ability to learn and adapt, which you mentioned already as an important aspect of intelligence, and the ability to understand. This definition is, by the way, by Legge and Hutter. It was published in 2006. So now I would like to come to the point to define what artificial intelligence is. I'm presenting you 4 possible options, which I would like to read all of them and try to choose the one that you think the best defines artificial intelligence. So I hope everyone had enough time to read these definitions. And if you know which one you would go with, then I will talk a bit about each of them without picking any of them as the best solution. So actually, all of these definitions exist and were given by respective scientists, and I'll show each of them now. So the first one, option A, was from Russell Beal, University of Birmingham, and kind of touches on the funnier aspect of artificial intelligence. But on the other hand, this is a widely perceived definition, and the one that actually stands the stress of time quite well. Option B is from John McCarthy, who was a professor at Stanford, and he's actually the very person who created the term artificial intelligence. And his definition actually goes on a bit more and says that it is related to the similar task of using computers to understand human intelligence, but artificial intelligence does not have to confine itself to methods that are biologically observable. So when we create intelligence in artificial manners, we can mimic biology, but of course, if we do it in a different way, that could still be referred to as intelligent behavior. Another funny thing that I would like to quote from John McCarthy is that he also tried to communicate about the thing that we saw on the previous slide. So that AI is something that we see on movies. And the thing he himself said was that once it works, it is no longer called AI. And we can observe this ourselves. So mobile phones were also called smartphones for a long time. We still might call them smartphones, but this kind of smartness is very natural nowadays. So it kind of just doesn't make sense especially for younger generation to call them smartphones. They just go by phones. And although the large language models were very astonishing, and to some they still are, but most people are getting accustomed to them. And now most people are not talking about how amazing the capabilities of these new generation chatbots are, rather how we can tackle the problems that are posed by their appearance. So option C is from Ray Kurzweil, who is a longtime AI proponent and a very strong believer in AI, and presently working at Google. And his definition is also kind of tries to be general as much as he can, but he can't avoid the reference to human natural intelligence. And option D is from Elaine Rich from University of Texas at Austin. And this again goes back to the very thing that option A mentioned, sort of, about movies, and that John McCarthy referred to as well. So in that sense, option B and C are the ones that are more precise or more engineering ways, but option A and D would be the ones that that people understand somewhat better. There are a bunch of other definitions, which I'm not going to talk about. Just I wanted to show you how many people actually try to define it. So with that, I think we can quickly summarize what AI is in a similar fashion as I did it for intelligence. And for this, I would say that AI is the synthesis and analysis of computational agents that act intelligently. And please do note the strong reference to the concept of intelligence here. So we can't get around that. And in the book by Poole and Mackworth, titled Artificial Intelligence, that I will also include among the references at the end of this slideshow, the definition includes science and engineering of understanding principles that make intelligent behavior possible in natural or artificial systems, and specifying methods for the design of useful intelligent artifacts. So the first point talks about understanding what makes something intelligent, something or someone intelligent. And the second one is about the engineering part. So the first one is the science, and the second is about the engineering part. When we want to create something, design it and create it. And all artificial intelligence systems can be thought of as intelligent agents. And we expect these intelligent agents to act according to the circumstances and the goals it was given, to adapt to dynamic environments and goals, to be able to learn from their experience, and to be aware of their own limitations, such as how much memory they have, or what is the expected response time they have to go with, or what reaction time they have to obey, for example, for an autonomous vehicle. Now, with intelligence and artificial intelligence, we talked about these as something that exists, something that is either intelligent or non-intelligent. But we all know that there are multiple levels of intelligence. So this is not a black and white thing. And if we look at different levels of intelligence, when we perceive humans and machines behaving in intelligent manner, then we see that these are actually different levels that can be done better or worse. And playing team sports or driving a car is not very difficult for a human person, at least for an adult. Playing chess or Go can be a larger challenge for some people, but these are actually way easier for machines than the previous two. And then we could also go on. Recognizing a cat was a simple task for humans for long, and it's already fairly easy for machines as well already. Computer vision systems really show signs of great intelligence. However, solving partial differential equations was way more difficult or required more intelligence from people, which is not a proper way to call, or this is not a proper reference to the concept of intelligence, or not general intelligence at least, but was easy peasy for machines for a long time now. And we could also talk about logic puzzles. But what I really want to go towards is the concept of differentiating between machine intelligence and human intelligence. And although this seems to be something fairly easy to start. But if you think about, I mean, given the different levels and aspects of intelligence that we mentioned earlier, but if you think about animals, then animals actually do possess a lot of intelligent behavioral aspects that they share with us humans, but they do lack a lot of others, like, for example, the ability to play chess. And even if you think about children of different age and the feats they can achieve, it seems that intelligence is a very layered thing. And here I'm also citing Moravec's paradox, who published this in 1988, and who said that things that are easy for humans are difficult for AI and vice versa. And although with the appearance of newer and newer AI systems, this landscape is slightly changing, but the general difference between human intelligence and machine intelligence has not disappeared. So if we want to visualize this hierarchy of different levels in AI, then this is one possible approach with just as minimal number of levels as we can put here. But at the bottom level, we will have all the classic AI approaches, and that we will shortly touch upon in this course, and machine learning, which is in the forefront of AI research. And at stage 2, this arrives to a more advanced level, and we think about technology currently being at this second stage. And the top stage here concludes the pyramid by saying this is achieved when machines become conscious. But when can we say that a machine is conscious? It's not easy to define. As difficult as to say when we observe intelligent behavior. So scientists actually started thinking about this a while back, and the first person I would like to mention is Alan Turing, who published the Turing test in 1950, and this intended to create something that can differentiate between a human and a computer based on intelligence. This still did not explicitly address consciousness, but of course we do need something in our hands about intelligence to be able to talk about consciousness. So in the drawing, you can see the envisioned situation by Alan Turing, which included a computer and a human person closed into 2 different rooms, each having a connection, a computer connection where they can use a text chatbot to talk to another party. And this other party was actually imagined by Turing to be a judge, who is denoted by letter C on the drawing on the right side. And the judge in the Turing test is tasked to tell apart which room has the human person and which room has the computer. And he is allowed to chat with both of them. And based on the answers of the 2 agents, he or she has to decide which is the computer and which is the human. And this was a genius idea, and is actually still sort of in use. However, with time passing by, some limitations of the Turing test actually showed up. So, and today with the appearance of large language models, Turing tests have mostly become dysfunctional. So it has become very, very difficult to differentiate based on just textual answers, whether you are chatting with a human person or a computer. So here I'm stepping for a moment to ask if there are any questions so far, because with the definitions, probably they might be not very clear. Maybe they weren't clear for everyone, but these concepts are just basically proposals. But now that we are coming to more specific things, I will try to make sure that everyone can follow along. So I also see many of you posted your answers for artificial intelligence definitions, and C came out as the most prominent one. And if you happen to have any questions, just please do post them in the chat, and I will stop then for a moment to try to address them. So stepping ahead, I would like to show you another quote from a scientist, an American scientist of Hungarian origin, Norbert Wiener, who published this in 1960. So still in the very early ages of computers, where keyboards were still rare, and it was kind of natural to refer to them as mechanical agency, which is sort of similar to an agent. So what he said is that if we use to achieve our purposes a mechanical agency with whose operation we cannot efficiently interfere once we have started it, so basically in today's terms, we would say that if you create an AI and let it go, because the action is so fast and irrevocable that we have not the data to intervene before the action is complete. So if this AI is fast enough and has the ability to do various things, then we had better be quite sure that the purpose put into the machine is the purpose which we really desire and not merely a colorful imitation of it. Now, this quote actually has a message more about us humans than about the AI itself. What is the primary message in here? Shortly, is that we better always make sure there's a big red button which we can push to make it stop if something went wrong. Why would things go wrong? Or what do we mean by things going wrong? Here we mean that for humans, we are used to define things and interact with each other at the same time. Mathematicians might be the most precise. The people who are mathematicians might be the most precise type of humans, or have the profession with the largest inclined towards being precise. But even mathematicians do make a lot of mistakes and commit a lot of loosiness at first, and they interact with one another to try to correct those. Now, if we ask a machine, which we expect not to commit loosiness and follow the instructions that we give to it exactly, then a large level of carefulness is advisable. This is the primary message of Robert Wiener. If you ever tried to write a code, then you probably remember that you did mistakes. And if you have never tried to write any code, then just think about how many times people didn't understand you at first and they had to ask, or they misunderstood what you said. And this can even happen with lawmakers who try to define everything extremely precisely and then have to fix the law a number of times in a lot of iterations, because it turns out that people will find, people are intelligent enough to smart the exceptional case and turn the law upside down for their purposes. And that allows us to arrive to consciousness. So this was discussed by a lot of scientists even before 1980, when John Searle, a philosophy professor, published his paper called Minds, Brains, and Programs in the journal Behavioral and Brain Sciences, where he argued that a machine can never become conscious in the sense that a human person can be. And for this, his main argument was the Chinese room experiment, where he envisioned a machine that was smart enough to be able to communicate in Chinese fluently at a level at which it was impossible to differentiate it from a human person. And actually, that was still just a futuristic thing to envision at the time. But some 40-something years later now, it is kind of reality. Or even if it's not impossible, but it's very, very difficult to differentiate. But he imagined this to communicate in Chinese, maybe for the reason that he was not a native Chinese person. And I'm not sure if he spoke any Chinese, but definitely was very, very beginner in terms of Chinese, even if he did speak some. And he said that if such a machine exists and it is locked in one room, then he can go into a neighboring room with a door between the two, and then take the code that the machine is executing, just print it out, and having a lot of books around, and maybe even dictionaries if he needs some, and then he can just follow the instructions of the computer step by step, exactly as it is programmed into the computer. And whenever he gets to the instruction where anything is printed, then he will just draw the letter and put it on a paper and slide it back underneath the door. In this way, they will be able to start communicating. So the machine can send him messages and he can send messages to the computer in Chinese. But he admitted that in this process, he wouldn't consider himself understanding any of what he's saying. And he argued in this way of communication, it cannot be called consciousness. And for the very same reason, I mean, this was his primary argument, in that even if computers can behave in an intelligent manner this way, they still cannot be called conscious. Okay. So I see that some people are asking for the copy of the slides. I will share the slides. I will make a short break in a few minutes, and then I will share the slides so as you can use them to make notes. And sorry for not doing this before the talk. So basically, this kind of arguments talk are somewhat related to what is usually referred to as weak AI and strong AI. So whereas weak AI is something that is able to perform a specified task in a given environment. For example, chatting about various things in Chinese. A strong AI would be something that would be able to show the signs of intelligence in all sorts of environments. Now, in this first part before the break, what I want to touch upon a little bit is the relationship of artificial intelligence and deep learning, which has come around about 10 to 15 years ago and was basically the most important precursor to large language models. So if you hear about deep learning, you might ask this question: is artificial intelligence and deep learning different? And they definitely are. We can't do everything with deep learning that we could expect an AI system to do. And the most obvious proof of that is that we can still think in a more intelligent fashion about deep learning systems than deep learning systems can think about us. At least this is what we understand and believe. And there's something that is still seriously lacking from current AI systems. And this is what is usually referred to by System 1 versus System 2 thinking or learning. This is from, you can see the reference down there. Originally, this was proposed by Daniel Kahneman, and then later on picked up by Yoshua Bengio. So this is mostly, if we want to characterize this proposal, what they call System 1 and System 2, then we could call the former an unconscious way of thinking and arguing, and conscious for the latter alternative. And the first one is intuitive and fast. This is what we basically do without thinking. And the second one, System 2, would be that is logical and slow. And the first would be more habitual for a human person, whereas the second one would be more kind of algorithmic, so that we can write the actual steps down and needs some planning and reasoning. And at the moment, most AI systems are actually more System 1-like systems. They can act intuitively, so combining in a quick and easy fashion. And this, what I'm claiming here, mostly applies to deep learning and neural networks. There are other AI systems that actually follow System 2 learning, that follow logical and slow inference processes, so drawing conclusions from observations. And they also have the difference that System 1 approaches can go wrong easily, so they do make mistakes, similarly to human intuition. Whereas System 2 approaches make barely any mistakes. So because they are machines, we can program them to kind of get rid of making mistakes, or if that happens, we can still detect them. And in that sense, a system 2 thinking for machines can work more reliably than system 2 thinking for people. And this might be one of the aspects that I was earlier referring to when I discussed human intelligence versus machine intelligence. And we talk about deep learning, then this system 1 type of thinking is deeply inside the way these machines operate as of now. They lack a number of things. For example, transferring knowledge to other domains. So for tasks that they were not taught for, they are not able to show signs of higher level cognition. They typically are not able to apply first principles type of thinking. So going back to very basic principles that we learn in school. And from the agent perspective, they are lacking causality. So many times they don't understand what is the cause and what is the result. And they have some attention constraints, and therefore we say that even if some might argue that this behavior already shows signs of consciousness, this consciousness is still fairly limited. So you might observe here that I didn't define what consciousness is, and that was on purpose. I don't think I'm able to define it, but I'm relying on your intuition into understanding what you mean by consciousness. And before we go to the break, I would like to continue on this argumentation, what is still missing towards a human level AI. So real understanding of language, which seemingly, even with the appearance of large language models, does not happen. Integration of learning with knowledge. The newer generations of LLM systems actually try to make steps in that direction, but this is still very limited. Long-range thinking at multiple levels of abstraction. Similarly, this is something that the newest iterations of LLMs are trying to do, but I mean, these are still early baby steps, and you can easily drive them off their rails. And cumulative discovery of concepts and theories. So these were all proposed by Bertrand Russell, and there is also actually a number of others by other people, but just to give you a glimpse of what's missing still in AI, I think this should be enough. And to give you something for the break, I wanted to introduce one further scientist called Mikhail Moiseyevich-Bongard, who published the since then so-called Bongard problems in 1967, which is something that is really exciting in terms of how you perceive intelligence and finding your way of intelligence. These are all connected to vision because they contain figures, but they need way more than what is enough. I mean, they need more than just visual intelligence. So he proposed the task to solve such a problem. The task is to describe what is the common property of one set, so the 6 figures on the left side, that is not shared with the 6 figures on the right side. And for us humans, at least who finished at least elementary school, this is a no-brainer, at least this problem. And if I show you another one, this would probably even very easy for children who haven't even started kindergarten. However, programming a computer to formulate the property is a very much non-trivial task. And if I give you a Bongard problem with a larger ID, then you might find yourself thinking about what exactly the differentiating property between the two sides is. So if you think you know what the solution is, please push the raise hand button. Okay, I can only see a single person. I'm not sure if this is because this is so challenging or because the network is not that well, or you still need more time to think. Well, I will still wait a few seconds. Okay, still only a single person. So I'm not sure, would you be open to share your solution with the others?
Yes, I can share it. So probably it has different solutions. My solution was that on the left we can see clearly 4 lines divided by intersections.
Mm-hmm.
And on the right there are 5 lines.
Exactly.
And we could say that, for example, on the right side, on the left bottom, there are just 3 lines, but because of the intersections, they are still divided to 5.
Mm-hmm. Yes, exactly. So there's some challenge in defining why the left side is characterized by the number 4 and the right side is characterized by the number 5. But with appropriate definitions, we can actually come to being able to explain that these hold for all of the figures on both sides. So either we call them intersections or junctions. There's some way of defining them, and this is already a way higher level of puzzle than the previous ones. So now that I explained what Bongard problems are, I will leave you with this one for the break. So everyone has time to think about if they can figure out what the shared property on the left side is that is not shared by the ones on the right side. And if you think you know what the solution is, then try to define the concepts you used in your definition. So I think the break will be 10 minutes. So in 10 minutes, I will resume from this point. And I think we can stop the recording for the break. But if not, we can just cut it out later. Okay. So unfortunately, okay, so I think it's time to resume. I think the recording is still ongoing. So I see three. How do I become muted? So I see that three of you have raised your hands. I would like the first person, Igor Stepic. I'm sorry if I'm not pronouncing the name well. Please, if you can go ahead and ask. Oh, okay. If not, I'm not sure if you are raising your hands because you want to ask. But now I would proceed to George Chantzis or Chantzis. I'm not sorry about the pronunciation.
What my thought process was is I viewed the shapes as if they were faces. So looking at the left side, we can see there's a point where looking at both sides, actually, there's a point where they become more narrow. So if we go according to that, in the left side, the dots are on the same side, whereas in the right side, the dots are on opposite sides.
Yes, I think this is the one most people come to if they can come up with a solution. And have you also thought about how you would define narrow?
What comes to mind is the way our body is built. For example, there's a point, our neck, where it's smaller compared to the rest of our body. That's kind of my thought process.
Yeah. Well,
Use them as necks.
yeah, absolutely. I don't want to push you. I mean, I think everyone hopefully understands what we mean by narrow, and referring to a neck is a very good analogy. But defining it exactly, it's not impossible. So you can actually define it more precisely in a mathematical fashion, but it's definitely not something that would be easy to do if you are not familiar with more complicated definitions. Okay, so well done. Does anyone else want to share something related to this? So I have also Arthur Shahakian.
Yes, at first I was thinking about the convexity of these sets, but I noticed that they are non-convex, all of them. But when I compare the left side to the right side, on the left side, both points are on wide or narrow side, while on that one, on the right one, they're like on two different sides. Like on left one, they are either on narrow or wide parts. Yeah, on that one, not like that.
Yes, absolutely. Okay, so this mostly coincides with the previous definition. So thank you all for sharing yours, and I hope many of you have found this exciting and challenging. So I also wanted to say that because of the lack of technical ability for me to share files on Teams now, I have posted a link to a URL where you should be able to access the lectures. I see some nice feedbacks, so I assume this should be accessible. And please let me know if you have any further requests or questions. There was one question about recordings. They will become accessible, and the University of Rijeka will provide these links for you. Are there any recommended literature that follows this subject? So in the end of my talk, I will mention some of them, and they are also included in the slides, which you can already access. So let us proceed with the lecture then. There are further Bongard problems. This is one that I think should be fairly easy for any human person, but would require a very high level machine intelligence. So in that aspect, this is one of my favorites, actually. So I hope if I tell you that the solution is centered around the concept of 3 and 4, you don't feel betrayed here. So, but defining what is exactly 3 and 4 is way more challenging, although should be very, very trivial for most human people. Okay. In the notes, you will also find one final Bongard problem, which I'm not going to ask anyone to try to solve here. But this is actually one where I think about 80% of humans give up before they get the solution. And if you like challenging puzzles, you can take this one. But you will see that not all Bongard problems are easy. So this is a really challenging one. Okay, and with that, I would like to go a bit further and start zooming out to give you a perspective on what do we encounter as we start going closer to AI systems. So what do we need to be prepared for? And these could be actually conclusions that I could tell you at the end of the course after having observed a lot of problems. But I actually think this is a short course, so I think it's better to flash a light on these problems up front. And even if you don't understand the depth and nature of these fully, they can still, I mean, I will and can remind you later that, okay, here we are, this is something we talked about earlier. So in my view, one of the largest problems that we many times bump into is called exponential blowup. Exponential blowup stems from the definition of the exponential function. And I hope most of you did learn this in school. An exponential function is something like 2 to the power of x, which means that it grows fairly fast. But for most people, actually, if you draw 2 to the x or x to the power of 2, okay, many might remember that the latter one is a parabola. It's called a parabola, whereas the former one is not. But not much qualitative difference is observed as a layperson. But eventually, if you have the changing quantity, the variable in the exponent, so like 2 to the x, for example, then this causes way larger problems than polynomial functions such as x to the power of 2, x squared, sorry. So, and how do we end up with exponential functions? Why are these coming up all the time? So what is actually 2 to the power of x? 2 to the power of x is just It means that we multiply 2 by itself x times. It means that if we go x steps and in each step we multiply the result by 2, then if we start by 1, then at the end of the walk, we will arrive to 2 to the x. And this kind of multiplication in every step is a very typical thing to happen. Because once you go a further step, if you have 2 further possibilities in that step, then you can multiply those 2 possibilities with all the previous possibilities you had earlier, and therefore the number of options you are faced with will be multiplied by 2. And if you have more than 2 options, then it will be a larger number, but the exponential nature will still remain. So this is one of the cornerstone problems in artificial intelligence. So we end up with very large numbers, and there are so many possibilities that it's very hard to choose from or find the good solution among all those possibilities. Another one, or the other one, because I will also only mention 2 of them here, is the representation of information. When we talk about intelligence, then we try to formalize the problems many times in a way that the machine that we want to work on it can actually take it as an input. Or even if we ourselves want to solve a puzzle or a mathematical exercise, or even just an everyday exercise, many times the way we try to think about the problem will influence very strongly how we can solve it, our ability to find good steps towards the solution. And when I say how we think about a problem, it is basically a kind of representation, which the best thing to do if you are trying to solve a problem is to visualize. If you write it down or you draw it down on a piece of paper or in a piece of code on a computer, then you will understand what the relationships are in the problem. So for example, if you have a pairing task where you have to find a nice hat for each of the people in a group, then to find a good solution, you can actually represent it in 2 alternative ways. Either you try to assign 1 hat to each of the people you have on the list, and then you have a list of people, and for each of the names you will put a hat. Or you can go the other way, and you can put a list of hats first, and then start assigning people to the hats. And this is a very different point of view. And although in this simple example, it might not make a big difference, especially if the number of hats and people are the same. If they are different, then of course the solution will be the number of possible options you will have will become different. And if there are more hats than people, then for some hats you will have to write no one, or you can just skip them. And if you use the list of people, then of course some of the hats will not be assigned, but that's not a big problem there. But you can already observe that the way we look at it, which we call the representation of the information, will be different. And this pops up all over the place when you try to do AI. Just one further example here about computer vision. When we observe our visual environment, we we humans, we do have a natural representation, which is encoded in our biology. Our retina has specific receptors, sorry, and that will encode the information, and it will be further transformed the way our brain is encoded to do it. But when you do a computer vision system, you have to decide what resolution do you want to use, and what color space you want to use. So there are technical factors that already come up as a difference. And also, this is just so-called low-level pixel representation that most of us are familiar with. But there are various other ways to represent visual information, some of them way more abstract than this one. Okay. Now, a few words about methods. So now we saw that what typical problems do we encounter along dealing with AI systems. And there are high-level answers to these. So one method is called the analytical method. So basically, this is what you could think about as the way you did in math. So you try to represent your problem with symbols and then use symbolic algorithms to operate on those and get the results in terms of some other symbols. Then there's so-called empirical or numerical approaches, where basically
Έσβησε η μπαταρία. Πού να το δω.
Basically, we just try to measure things or represent with raw sensory information, and then learn whatever needs to be done without having too much of a theory. And a combined approach is what typically called a hybrid approach, where we can combine the two.
Μου ζητάει register.
I will try to mute the person who's talking. Seemingly. Okay. Well, if you realize you were the one, then please mute yourself. I will just proceed now in the lecture. So at this point, after addressing the challenges and the methods, I would like to conclude today by giving you a very brief history in AI and an overview about the field. So things mostly started at around the time of Alan Turing that I mentioned earlier by publishing a Turing test. And then just 5 years later, Simon and Newell proposed the so-called general problem solver, referred to as GPS. And today we think about something else if we say GPS. And 1 year later, in 1956, Joan McCarthy, who is the professor I mentioned earlier related to definitions, coined the term AI at a conference that he organized in New Hampshire, in Dartmouth College.
Conference, το παρουσίασε σημαίνει conference. Αδιάλεξη, μπράβο, conference, μπράβο.
I'm not sure if Sandy, you could please help me with muting the person who. I cannot mute
I've
myself.
tried to mute them all, and
okay, thank you. And now I muted myself. So okay, with these Teams meetings, this is definitely a challenge. We could do a webinar, but then the rights would be way more restricted. So let's proceed. This is a brief map or a tiny map of the first 3 stages in AI history. The first one, which is called the inference period, where these classic symbolic approaches appeared, basically mostly building on logic. And very, very similar to what philosophers were doing in the field of logic earlier. Then a second, and then the first AI winter came about when people realized that this will not be enough to make large intelligent systems. And then a second stage came about, which we refer to as the knowledge period, where the appearance of expert systems could be witnessed, and more importantly, the breakthrough of neural network with the appearance of algorithms that were able to train neural networks that were artificial neural networks that are mimicking the human brain without inputting any high-level representation of the knowledge, just the input and the output we wanted to see, and then these neural networks have become able to learn from examples. And that was an era of very large enthusiasm. So whereas in the first stage of AI, most of the enthusiasm were still towards computers, at this stage, computers were already more, at least inside the scientific community, they were widely known and accepted. There were no real personal computers at the time, or only in a very limited amount. But with the ability of doing these breakthroughs, this was a very large enthusiasm inside the community. And that ended up with the second AI winter, when people realized that even though for toy problems, for very small things, these new approaches worked wonderfully well, when they tried to scale it up, they stopped working, or they have become incredibly slow. And in the third burst, which we call the learning period, people realized that the methods were somewhat lacking from the previous AI stage. So some new theoretical advancements had to be made. But most importantly, the 2 or 3 decades that have elapsed between the two actually increased the available computational power large enough that many of the problems could be tackled that were not possible beforehand, just by doing the very same thing in a brute force fashion. But of course, the real breakthroughs came here, not because of this, but extending the approaches in terms of theory. And that ended up with the breakthroughs in deep learning from the early 2010s. So this is just a quick overview in a textual manner. I think I can safely jump this. And on this slide, you can see the 2 main schools that I mentioned earlier in terms of approaches. On the bottom are the so-called numeric school, the ones belonging to the numeric school, namely including neural networks as their most important representative. Whereas in the symbolic school, you see a number of different approaches that mostly are concerned around different logic representations. and some further machine learning approaches, including decision trees, which you will hear about throughout this week. And we will see how they were used to do simple systems in AI. But this is still a fairly limited number of concepts that pop up in AI. And every year, a number of new concepts pop up. And with so many concepts, even the ones who are inside the field start to get confused every once in a while. Luckily, there are business ventures who are think tanks who try to summarize this all. And Gartner regularly publishes their understanding of the most important concepts in a number of fields, including AI. And you can see that they not only gather these concepts, but they always put them on a so-called hype cycle, where they try to see what are the newly appearing trends in the field of AI, what are the ones that have been around for some time and running up, the ones that are on top of the hype. Here you can see generative AI sitting on the very top, and this was compiled for last year, but I think for this year it still has not appeared. And then you can see others that are kind of post-hype, which have already passed this highest phase of interest from society, where the expectations are very high, but the actual deliveries, so the results are not living up to these expectations yet. And then here, after some disillusionment, those concepts and approaches that make it to real applications will eventually come to get spread and then widespread, where they finally reach the plateau of productivity. And connecting back to the definitions, I have to say that this is where we humans typically stop. In the field of AI, we typically stop calling them intelligent. So these are novel things appearing in AI, and ones that have recently approached or achieved maturity. But there are a number of ones that have reached this stage way earlier. And I just want to quickly highlight some of them and related sciences that use AI for their own purposes or to make advancements in their own fields, but are not considered strictly AI, including mathematics, psychology, linguistics, biology, and philosophy. I started by computer science and data science because AI is considered to be a subfield of these, whereas data mining and machine learning are considered to be subfields of artificial intelligence itself. So, but these are also kind of related sciences. And these these sciences create applications in a number of different areas, where basically I've just put a couple of them here. I think most of you are familiar with the appearance of AI in these fields, and there's a reason you are interested in studying AI, although they might not be as apparent in some of these as in others. So I could have put discovering drugs, for example, has strongly shifting towards using a very large amount of AI tools. So this is not exclusive list by far, just to give you a glimpse of where the AI can be used and is used in industry and arts as well. So the branches that have been actually detached from AI earlier are these. So the ones I mentioned earlier, including machine learning and deep learning as a subfield of machine learning, and then computer vision that deals with processing not only still images, but even videos, and with generative AI, not only processing them, but generating them. Then speech recognition, and similarly, we could include speech synthesis here. And our phones, we accept our phones talking to us with synthesized voice. And if you go online and watch videos, many of those videos already have synthesized voices without us being able to even realize it. And you can just thank the author if they are transparent enough to declare that the voice is synthesized. And the same thing is for actually videos as well. And then natural language processing, which tries to go towards understanding language, which of course tries to go towards consciousness. And these are two things I've mentioned earlier. And expert systems have been very popular, as I mentioned earlier, in the 80s, and are still around and used, for example, in many cases for in the medical field and even in the legal field, but they are not really considered as AI systems anymore. Again, underlining or reassuring this kind of changing definition of intelligence, and especially AI in our minds. And here you can find the textbooks that are most widely used and that I can propose. Many of these have a link where you can access them online freely. But most of them expect you to have some kind of a formal background, but not very much. So especially with the Russell Norvig textbook, you can actually pick it up along the way as you're reading the book. The others are a bit more technical, but I think they are still a good, worthwhile source of knowledge for as reference books. And with that, I would like to come back to the questions that I've put up at the beginning. So I think we kind of, at least sort of, managed to define what intelligence is and what artificial intelligence is. So those are included in the slides, but there are a number of other questions that we didn't specifically talk about. So how does it work is something I promised to discuss along this course. So the whole purpose of this course, and actually of the whole program, is to talk about how AI works and how to create AI systems. So even though we are going to address some of the basics here in this course, many of the others will be addressed in other courses. How to control, repair, and improve it. So going back to the quote from Robert Wigner, it's important that we create AI systems over which we can retain some control. Or otherwise, we better make sure that the upfront goals are very well defined, which I tried to hint at that I think it's impossible for us humans. So my opinion that keeping control over them is not really an option as of today. How about repairing and improving them? What do we mean by repairing an AI system? So it's about if you have control, then you should do something when you observe something unexpected or unintended about the behavior of an AI system. So you can call it reparation or adjustment, but this is definitely an iterative process in almost all of the cases. And this is typically can be done in two ways, either by, if you have a good understanding of the internals of the system, then an expert can find out where the internals have to be adjusted and make an informed change in the machinery. This is just like what classical car mechanics or what you would expect a service to do to any of your machines. However, in AI systems, in many of the cases, we don't really understand what's going under the hood. So to repair it, we actually need to fix the specification that was input when we created the system. These are typically systems that learn themselves, and we have to give them new samples, new examples to learn from those, which we kind of forgot about when we initially started training them. And this also applies for improvement, but improvement doesn't mean that they gave an outright bad answer, but maybe the answer or their behavior could be better. So actually, the methods for fixing or repairing and improving are fairly similar. And then there's this group of questions. So what are the consequences? Do we need to be afraid of AI? First of all, I have to tell you that I don't have provable answers here. So there are many opinions, even inside the community, but I will give you mine. So first of all, in my point of view, it's always better to be afraid than to get scared. But is there a reason to be afraid of AI systems? The most important concept that you might hear related to this question is called today alignment. Alignment means that when we create AI systems, we should create them in a way that the goals that we put into these systems are in alignment with our goals, with the goals of humanity. Now, we could address the question whether humanity as a whole has a well-defined set of goals, but at least if we say that we want to align machines with humans, then we should, and we can, I think we can accept this as an assumption. So there are large efforts towards making these AI systems, today's AI systems, aligned with human preferences. And I think it's important to do it, but I don't think there is an imminent reason to be afraid of AI systems. I think it's way more important to try to domesticate AI systems, as we did with animals, and to put enough effort into the alignment and regulation of these systems. But I'm pretty sure that challenges and problems will come, and we will have to face these challenges and problems. And these are going to be, in my opinion, very different from the ones we have solved so far. So being prepared and understanding what kind of challenges are coming up is very important. Then second, will AI replace people in my profession? I think this is a very natural fear from people on our side. And actually, the answer for this, again, is very different from many different experts. And whereas previously they said that mechanical jobs will be replaced first, and those who are very smart, like engineers and computer programmers, will be very hard to replace. Now, the landscape has changed quite a lot. It seems that physical workers are not being replaced, whereas a lot of IT people were laid off in the past 2 years. But I still think that computer engineers also will be required. And even if some of the jobs will be replaced by new AI systems or robots, this will create new jobs. I mean, we have already observed this and witnessed this with the Industrial Revolution and have been witnessing this ever since. This might get a bit more rapid, but I don't think humanity as a whole, I mean, this would be the largest challenge as of now. And finally, what can we do, or what can I do, and what can you do? I think one thing you can do is to study AI. So that's a good point already. And to pay attention to what's going on and initiate discussion with those who have less understanding than you do, or with those who you know should have understanding, like decision makers, which you might be in contact with as of now, or you might get in contact with later. But definitely, I think the discussion on the level of society is an important process to do. Okay. And I know your upcoming class will start at 5 o'clock, so I don't want to stretch this too long. But because of LLMs as being the current thing and the present thing inside AI, I want to end this lecture with some comments and suggestions on the use of large language models. And this was the reason I started with these two. So there are very large challenges with the appearance of LLMs. So at universities, for example, many of the students think that submitting assignments that have been solved by LLMs is fine. And I think teachers should somehow adapt to that. The problem is that this will not facilitate understanding. Or if it doesn't facilitate understanding, then it will have serious consequences of those who start using them without making sure that they review the outputs. And if we try to use it for learning, then try to use it for learning. Of course, the temptation, if the deadline is close, can be very large to use LLMs without reviewing the output. But I think first and foremost, try to withstand the temptation. So it will have long-term consequences if we as a society don't learn how to resist that temptation. So I think what is important about using LLMs is to understand their working principles. Okay, we have a microphone problem again. Hopefully this will be solved. So try to understand their working principles. We will talk about that. Understand the way they represent knowledge, which in short is just embedding vectors, which I don't want to explain today, and understand their limitations. And even if you are not an expert, this third point I think this applies to everyone. And if you want to have your hands dirty in using LLMs, then get experience with using the new tools. So try Copilot if you do coding, and if you haven't tried it yet, or whatever similar tool. And do try the new apps that come up. I see many people giving talks about AI without trying the tools that these AI tools actually enable. So I'm actually personally also struggling with trying all these new tools, but I try to keep up with the flow. And only say opinions about things you tried yourself. And try it on your own task. Put it to your own challenge. And then that will allow you to discover the limitations and the possibilities much better. So first, last but not least, try to improve your workflow by using LLMs. So I think this is very important because there are many ways in which they can make you more efficient. But some level of carefulness is always required. But the best way to go is to make them your ally instead of your enemy. And with that, I would like to thank you for your attention, and we will continue from this point tomorrow. If there are any questions in the remaining time, I would be very glad to answer them. Okay, I see a number of appreciative comments in the chat, and hope to see you tomorrow. And if the question in you comes up later, don't forget to write it up or email me right away. So then I will stop sharing and